suppose that everything should be fine. So welcome everyone. I think it's our 10th course. Yeah, we plan to have 3 more. Yeah, if nothing strange will happen. Yeah, because we are missing one, but we are ahead of time. So, and I suppose that you have enough material and work to do. So I think it's just good to go that way. Yeah. Of course, we could organize maybe one extra meeting just to consult results, yeah, or just to discuss about your assignments, or maybe especially those larger ones, yeah, if you want to progress with them. But we'll base this on need basis, yeah. If everything go fine and everybody will be happy with their grades, which is not very likely, then no issues, you know. If not, then depending on how many of you won't be satisfied, then we can get get back to it. But okay, but now we are here, yeah, and we are continuing our development in computer-aided analysis. Uh, and again, most of the slides are the same like last week because we are still on the topic. Yeah, we are progressing. Yeah, so today we'll finalize our kinematic solver. Yeah, but still we are there. So I just put those things for reference. However, as you can see here, I put the information about assignment, yeah, and I simply wonder how are your, if you have any questions, doubts, problems, because there are some questions, yeah, so. Yeah, I just try to find this on the YouTube because it's something super strange because it looks like it's streaming, it's broadcasting, but I cannot see this. Okay. Now I can see that it's ongoing. Yeah. So sorry about that. Yeah, I just will start uh, to see chat muted and yeah, perfect. Yeah. 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 This is one possibility. Yeah. For the people online, the question was about how to get 5.0 for translational joint. Yeah. So you can do this in many ways, of course. Yeah, unfortunately. Yeah, fortunately, unfortunately. Yeah, the easiest way would be to ask about the relative angle from the user and specific directly. And I'm not sure why do you want to ask user again? Yeah, that's true. Yeah. But it depends how are we sure about those initial coordinates. We discussed this already, yeah? So, and we already make this kind of this once, yeah? So if we will get to the code, yeah? Like, if we have simple constraint, for example, because revolute joint, okay, we are providing those points, yeah? Uh, Note that for a revolute joint, we could also do this different way because we could force example, assuming that we know exactly how the joints looks like, we could just ask user for one point that is global point, and then we could calculate those local points. Yeah. So this is another thing, yeah. But here in general, we were assuming, yeah, that those initial positions may not be exact. So that's why, for example, the same what you ask applies to simple constraints. Yeah, because we either could provide here, like we are providing the constant values, or we could took them from the previous data. Yeah, but here we decided that we'll just ask user, take a look on your mechanism and just provide it. Yeah. So I would suggest that we will to just ask user about this angle. Yeah. And of course, like it's shown here and as well shown in the book, there are those two angles. Yeah. But those are constant, so you can just ask about one angle. This is just relative angle. Yeah. So this is maybe once again, this is only one way of working for it. At least now I can see where it came, because I haven't read it for a while. But it's already based on this ND, yeah. And of course, yeah, because there was also a question, all this is in a global coordinate frame, yeah, so we have to transform it to global coordinate frame to make it work, yeah, simply because it doesn't have to be entirely global coordinate frame, it can be any coordinate frame, but to make it work, all this data must be in one specific coordinate frame. And it makes the most sense to make all this in global coordinate frame, yeah, because then whole vector of C is in a global coordinate frame, so we can work on it. Yeah, if so, in practice, it must be in global coordinate frame. Yeah, so all already those coordinates that are here, they do not have bar, uh, prime, or whatever signature. So it means that all of them are already in global coordinate frame. Yeah. So I didn't like it that it's shown here on the base of coordinates. I would prefer that it's just on the base of uh, vector notation, because I don't understand why. But okay, yeah, it's author choice, and of course it's valid. But okay, so this was a little off topic, yeah, about other questions. Uh, so here, okay, so just to conclude, yeah, here, in most cases it's zero. Yeah, like in our cases. Yeah, but of course, if you put, um, you could have some relative angle. Yeah, it's quite easy to imagine. Yeah, but I will ask the user. Yes. Yeah, of course. Yeah, all the levels, and the simple reason is that if you because once again, you are implementing missing features in our program, and it is meant to be general solver, yeah? So if you can analyze position, velocity, and acceleration level for our slider crank, yeah, then okay, because it's not yet implemented, but it will be implemented. But when you will be able to analyze position level for another mechanism by this definition, it should automatically give you velocity and acceleration level solutions. So it should cause no more work, except of that you should put more plots into the report. Yeah, so it should work. Any other questions? Okay, perfect. Okay, so very briefly again, yeah, if you did not yet memorize it by any way, yeah, so we are working on Cartesian coordinates. We have two transformations on the way. One is transformation of simply coordinates from one reference frame to another reference frame. Yeah, so it means that we just describing the same vector in two different reference frame, and because those reference frame for this vector are just rotated, it's rotational transformation. If you want to have position vector that is described by this kind of vector in the local coordinate frame, yeah, with respect to origin of the local coordinate frame, we have to add the displacement. from that, that differs between those two frames, and then we get this nice expression. We use this expression directly in revolute joint, of course. We use it on also, we could use it also partly here, yeah, because like we have 1 point here, 1 point here, yeah, it's similar expression, yeah, like we can go here, here, and then here, here, and subtract it, yeah, and we get this vector D. Vector N is versor, so it has some constant coordinates in local coordinate frame, then you have to just transform it to global coordinate frame by rotational transformation, yeah. And here, of course, we have those relative angles, yeah. But for our case, those relative angles are mostly 0, and it is the case for our example. For sure, this is 0, so you can ask the user to put there 0, yeah, and it should work. Simple constraints, just simple, keep something constant. Driving bodies, the same, just take one coordinate, whatever, and assign their function of time. Very easy on planar case, especially like we are driving some rotations, yeah, which is very common because most drives are rotational drives, very convenient. We discuss about this, and we are on the stage to implement position analysis, yeah. Then it will come time for velocity and acceleration analysis. We'll get into it very soon. Position vector derivatives. We have discussing this. Yeah. Here we have just coordinates. So we just get directly velocity position coordinates. Yeah, just derivative with respect to time, and it's solved. Here with rotations, it's slightly more complicated, but not really. We get this constant term, then the same expression, rotational matrix and vector. So this is in practice the expression for the vector coordinates in global coordinate frame, yeah, plus transformation, plus result of derivative, so phi prime. For second, it's slightly more complicated, but again, the rules are the same. This is our analysis. We know what we have we should have, yeah. So we have all that except of translational, which is your role, coordinates, and we are missing only that part, yeah. Like written here, yeah. We have solved position analysis because we are able to get coordinates. Then we are able to get C vector, yeah, and then we could solve it using fsolve, and it works. However, we want to go for Newton-Raphson because of two reasons, if you forget. So one, as written here, Newton-Raphson is faster. And second, okay, because some kind of a disadvantage of using Newton-Raphson is that we need the Jacobian of our constraints, yeah? But we need this Jacobian to calculate velocities and accelerations. So we still need it, yeah? So if we have already the Jacobian, we can use Newton-Raphson, which is faster, because, yeah, why not? And now we are at the stage of Jacobian, yeah? Because if we get back to our code, we do all that stuff, yeah, and now we are at the stage to use Newton-Raphson, yeah. So let's update our list, because in order to use Newton-Raphson, we need Jacobian. Then with Jacobian we can just use Newton-Raphson, and then with Jacobian and Newton-Raphson we will run because now all those steps gives us solution for t equal to 0, yeah. Then we have to wrap it up all that stuff and march in time, yeah. So we have to get this position, this analysis in time, and our last step will be velocity analysis in time. Yeah. And your role will be, as far as I remember, acceleration analysis in time. Yeah. But we'll discuss about this when we'll solve all those parts. Okay. Any questions? Or all this is clear? Okay. So Jacobian of constraint equations. Yeah. So we have here this function constraints that returns us constraint vector. Yeah. And in the same way, we wanted to implement Jacobian of those constraints. Yeah. Uh, so simply I will copy paste it firstly. Yeah. It won't be copy of constraints, but it will be Jacobian of constraints. Or do you want other way around, constraint Jacobian? Is it okay? Yeah, code is pretty. So fix the name. I will change it to CQ. Yeah, because C was our constraint vector, CQ will be our Jacobian because this is or J. Yeah, but let's CQ is fine. Jacobian of constraints. It gets, of course, definition of the system. Q and T, and that's all. Because for Jacobian, it's just partial C, partial Q, so we don't have velocities or other terms involved. Yeah, and that's all. Yeah, okay, that's all for definition. Yeah, so let's update. Let's update our description. Returns the matrix. Okay, which is partial derivatives. So it also means that this is incorrect, that uh, that the size is incorrect. What is the size of Jacobian? Do you remember? Because it's matrix, yeah, so clearly it's not a vector. Uh, so the first size is the same, because if you remember from definition is partial C, partial Q, yeah, so it is defined in the way. Do you remember how it's defined? Yeah, but okay, but the next size is number no, of coordinates. So it's the size of Jacobian is number of constraints and number of coordinates. Do you remember why? No questions? Okay. Simply it came from the definition. I don't know if this definition is here. No, it's not here. But it was partial C, partial Q. Yeah. So it means that for each constraint we have derivative in each column with respect to each coordinate. So that's why the number of columns is equal to the number of coordinates. Make sense? This also means, and this is one of the reasons why we would like to have the equal number of coordinates and equal number of constraints, because for this setup, Jacobian is constant, not constant, is square, exactly. So then we can just use it in Newton-Raphson, because Newton-Raphson involves solution of our linear set of equations. Another reason for that, yeah, because If it's not square, if it's rectangular, typically you can solve only the problem in the, for example, last square, solution. Yeah. So not the exact one, but okay. Yeah. And now we have to go through all our constraint types and implement this Jacobian. Yeah, as you maybe have noticed on the slides, yeah, I put how the Jacobian looks for revolved joint. But our first simple joint. As you can see, it doesn't really have. So I don't have slides for it. Yeah, but just this is just very easy. Yeah, maybe, but nothing is too easy. Yeah. So for simple joint, yeah. Okay, for simple joint we have C equal to it was some kind of coordinate. So let's say x I minus C. Yeah. So this is xi is some kind of coordinate, and C is constant value. Yeah. So of course it goes that way that qi is somewhere in the our q vector, where the q vector is vector of coordinates. Yeah. So we have some coordinates, and at some place we have qi. Yeah, that is connected with body I. And of course, as well, this C, it's, let's say, Cj, because if we have the vector of all our constraints, yeah, this vector, we have some constraints, then we have our constraint Cj, and yeah, it's just somewhere, yeah. And we can see this in the code, of course, yeah, that we just have this indices, which says where is this placed in our vector, yeah. All this makes sense? So, of course, uh, the only partial derivative in respect to the q that it's not zero for our simple constraint is related to xi. Yeah. So we can write that partial cj with partial xi is equal, of course, to 1. Yeah. So it also means that partial cj with partial q, how does it look like? Yeah. It looks in the way that we have zeros for all coordinates that are not xi, of course, because they are missing, so the partial derivative is 0. Yeah, this is also the reason why Jacobian is typically sparse matrix, so it means that it has mostly zeros. Yeah, so we have 0, then we have a bunch of zeros that at the position of xi, yeah, so at the index of xi we have 1, and then again we have 0, and up to the end of this vector we have zeros. Yeah, so we just have to put 1. So this is row vector, yeah, because this is row vector, but in general, all those partial constraints related to our core joints are in this form of those stripes, yeah. So the same like we are making our constraint vector just entry by entry, row by row. So the same applies to our Jacobians, yeah. We make it by rows, yeah. Just for C constraint vector, each row has 1 entry because it was simply a number. Yeah. And here we have all those vectors of the length of coordinates. Make sense? So how this manifests in our code? It manifests in our code that, of course, constraint indices is exactly the same as it was. Yeah. So because analogically, like we put constraint equations in the vector constraint equation 1 to up to n. Yeah. The same goes with the constraint rows for our Jacobian. Uh, and here we have the coordinate q, and we take this coordinate as coordinate index. So simply, at this coordinate index, we put 1. Does this make sense to you? Or this is a little unclear why we end up there. Is it unclear to anyone why this code looks that way and why it's correct one? Yeah. Yeah, of course, because this is this rule of consistency, yeah? That because we have to be consistent in our math equations, yeah? Because, all the coding comes firstly from math derivation, yeah? So coding starts, not at the keyboard, it starts, yeah, like here at the textbook or on the paper. Yeah. Okay, so maybe also slightly different because I cannot see that I have convinced every one of you. Yeah. So let's get back to our example. For example, like here. Yeah. So we get added 5 simple constraints, but let us just add 3 of them. Yeah. Or do you want to add all of them? Okay, but let us just add 3 of them. So if we want to add just 3 of them, it means that our Q, for example, is X, Y, and Phi. Yeah. And those are the coordinates for our ground. Yeah. Okay. So we had just one body, it's ground. It has coordinates X, Y, and Phi. Yeah. So it means that we have just block. Yeah. With our vector. Yeah. And with the Phi, I cannot here put Phi because I just put it according to the 0. So Phi is 0. But you understand. Yeah. And this is the ground. And we'll fix it, of course. Yeah. So it means that for this setup and single constraint, C is equal to X minus 0, Y minus 0, and Phi minus 0. Is it correct? Yeah. So how we have defined it? Yeah. So we can also write it in MATLAB notation that it's Q1 minus 0, Q2 minus 0, and Q3 minus 0. Is it correct? So we have 3 constraints, simple constraints, yeah. And in our code, when we have simple constraints, and when we are adding simple constraints, we are storing coordinate index, coordinate value, and constraint indices, yeah. So here, for this for the first one, if we were to add this, yeah, okay, so maybe I'll make it large and put it aside. So now we can see both, yeah, the code and that stuff, yeah. So here, of course, I will write a shortcut. So const id is equal to 1 because it's first constraint for the first entry, yeah. Then we have coordinate id is equal 1. It's here, yeah. So it's a coordinate id is equal 1, and of course chord value is equal to 0 because this is that one, yeah, that part. And this defined as a simple constraint, yeah. Same applies to second one, yeah, that constraint id is equal to 2, coord id is equal to 2, it's here, and coord val is equal to 0, and it's here, yeah. So so here you can see, how we connect our math expression to our implementation by keeping the track of our indices. Okay? And then, what is then CQ? CQ it means partial C, partial Q. Yeah. So for the first entry, we have only one. Of course, for all those simple constraints, we have ones only, yeah, because they depends only on one coordinate. And as we can see, the first constraint, yeah, so here we have C1, let's call it C1, yeah. It depends on Q1, so Q1 is coordinated in the first position, so 1 is here at the first position, yeah. So location in the row is guided by constraint ID. So we know that for constraint 1, constraint ID is of course 1 and so, yeah. So that's why we get this kind of, that all those parts are consistent, yeah, because, the way how we organize our coordinates is reflected in the way we create our Jacobian, and the way we organize our constraints also reflect in the way how we put the entries in our Jacobian. Just one reflects to row, another one reflects to columns, yeah. Because for the columns, of course, we put it according to our coordinate ID. Coordinate value is not seen in Jacobian simply because it's constant. Yeah, this part is constant, and it's just due to our differentiations, it just vanishes to 0. Yeah, so and because all the entries are 0, it doesn't matter. So it means for the simple setup, we'll have 1, 1, 1. Yeah. Of course, if you were to change the order of coordinate of constraints, it would look slightly different. But it must be consistent. So I hope that doesn't make sense. Doesn't make things a little clearer. So that's why we put here 1. Add constraint in this index and coordinate index. So, okay, so it's not working perfectly. So let's comment out the rest because it's clearly incorrect. Because it must be incorrect. Because it was the code from the constraints, not constraint Jacobian. Why I want to, I want to get back to MATLAB. Why I want to comment it back? Because now with this setup, we can calculate our Jacobian. Yeah, by the way, Jacobian doesn't depend on time, so we can remove dependence on time. So now here, after we run all this, yeah, we can calculate CQ is equal to of CSQ. Yeah. So let's run it. Hopefully without any errors. Yeah. So we have no errors. So this is just the old solution from this fsolve. And then we'll compare it with solution from Newton-Raphson. And here's our norm form constraints that showing that this works. And now I am expecting to see ones, yeah, in the first 5 columns, because firstly we add first 5 simple constraints. Yeah, the first 3 will be at the position 1, 2, 3 because it's ground. Yeah, and the last 2 will be at the very end, because when we were adding bodies, the bodies slider are at the end. Okay, and because we put our coordinates in the order of how we add our bodies, yeah, simply first is ground, so this will be at the first positions. Slider is at the end, so this will be at the end positions. Yeah. So this is what I'm expecting to get. And this is what I get. So no surprises. If there will be something surprising, yeah, we have to go back and see what is happening. Yeah. So no surprises. So for the first three simple joints, we get those ones, of course, here. And for the next two, we get them, of course, here at y and phi. Make sense? This is just programming. We could just mix and match this. Yeah. So for example, we could. mm, so this is not working. Can I move it? Okay. Let's say that I move it here. Maybe it's not the nicest solution because then, why? Yeah. On the other hand, why not? It's still valid code. It's the same mechanism because the solution that shouldn't depend on the order in which we put our constraints. Yeah. So this is exactly the same. And if you run it, we of course, okay, so something, I think that it's clearly not run because it hasn't updated. Okay. I suppose that I pressed the wrong button. Yeah. So as we can see, here we have 1 at position 5 because it was fifth addition to our vector. Yeah. And so it was placed from the first position to the fifth position. Yeah. Consistency is important. Yeah. Everything has to be consistent. Yeah. So the order we create C vector, it must be the same order we create CQ. Okay. But let's back to the original one because it just looks nicer and it makes more logical sense. But okay. And next, we are expecting to get something useful for our revolved joints. Yeah, revolved joints are slightly more complicated. So of course, the expression for the revolved joint Jacobian is also slightly more complicated. But it's not super complicated, and it's shown here. Yeah. Again, this is constraint equation, sets of two equations for revolved joint. Yeah, I hope that you already can recognize it. So they guide to the same vector, but from different local coordinate frames. Yeah. So that's why we have here this Ri, Ai, Sip local minus Rj, Aj, Sj, P local. And this might be equal to 0. Yeah. So now Jacobian is of course connected with velocity transformation because simply if we calculate velocity is also partial c partial q times q dot. Yeah, and this is also the reason why we need Jacobian for velocity analysis. So okay, so if we calculate part of the Jacobian, yeah, it takes this form. So here is partial CR, partial QI. QI means coordinates of body I, because for all other bodies we have only zeros. Yeah. And it's I and this omega AI SIP. Yeah. Like it's taken from here and here. Do you understand from where it came? Or is better to write it in more details? Okay, to be sure that we know from where it came. Yeah, so let's get back to those nodes. Yeah. So CR vector was equal to RI vector plus AI matrix SIP vector local minus RJ vector minus AJ matrix SJP local vector. Okay. here we are clearly connecting two bodies, yeah, body I that has qi vector equal to xi, yi, phi I, or it's also equivalent to ri vector phi I, yeah, and body j that has coordinates qj, rj, phi I, yeah. So partial CR, partial QK, and we assume that K is not equal to either I or J, is of course vectors of this, it is this matrix, yeah? This matrix has this size because CR are two equations, and QK for each body has three coordinates, yeah? So that why is this time 2 times 3, yeah? So only non-equals or non-zero terms came from Qi and Qj. So partial CR for partial Qi, it means that this is matrix where we have partial CR, partial Ri, and partial CR, partial phi I. Yeah, because it's in other terms, it's just we put partial CR with xi, yi, and phi I, and but yi, xi, yi, it's combined into ri, yeah? Or clear? So the only term that depends on ri in CR is ri, yeah? So this is the only term that depends on translational coordinates of qi, yeah? So that's why here we have, okay. So here we have partial ri, partial ri, because all the rest gives us 0. And here we have partial, with respect partial phi I of AI matrix times S dot IP. Yeah. That's true. Because this SI is constant, so we just get out of our differentiation, and the only term that depends on phi I is AI. Yeah. And now we know that, of course, partial Ri is identity matrix. Yeah, because it's identity. Because partial with respect to each other is 1. Yeah. So that's why it's identity. Yeah. Do you know what's identity matrix? Yeah. Just in case, this is of course 1, 1 in our case. Yeah. But identity is any matrix that have only ones. Yeah. And it's neutral element of multiplication for partial for matrix algebra. Okay. And we already have this on the notes somewhere that, of course, partial A with partial Q phi is omega A. Yeah, so it's simply omega. This is our constant term AI SI P. Yeah, and of course, the size of this 2 times 1. Yeah, so the size of this is 2 times 2. The size of this is 2 times 1. So the whole size is, of course, 2 times 3. Yeah, no surprises here as well. And that's all. And of course, if we make partial CR, partial QJ, we get a similar analog expression just with the minus, because those values, those part for QJ, like here, is done with negation, with minuses. And here we have exactly the same results. Yeah. And of course, it's connect with C dot, yeah, because simply C dot R if you remember from some algebra, is of course partial CR partial Q times Q dot. In practice, we are missing here one term, partial CR partial T, but this one is 0 in our case because we do not have the direct dependence on time. It will be non-zero term only for what? For driving constraints. Yeah. Does all this make sense to you and matches? Okay, perfect. So now, how to put this into the code? So let us uncomment that part. And of course, by analogy to this, of course, CQ is matrix. Yeah. So constraint indices are the same. We already know it. Yeah, because the order must match. However, now we also need the second part of the coordinates. Yeah. But simply we will simply we will write this Jacobian in two parts because we know that from here that the only non-zero terms comes from I and j. So body I and body j. So this means in practice that this part of the Jacobian is put it in this row on the position of qi. Yeah. So the first term came from the R body I indices. Yeah. And now we just will, rewrite this expression. And that is I of 2 and omega that we don't have. Omega times that term. Yeah, we already have it here because it's just part of constraints. So rotation of phi I times R as I local. Yeah. We don't have omega, so we'll add here. Okay, again something. Let's not make it complicated. Omega is just constant stuff, so it doesn't get any it doesn't take any arguments, and simply it was what it was, -1 0 0 1. Okay, so my memory is very good but pretty short, so so let's check it. 0 minus 1 1 0. So it's clearly incorrect. 0 minus 1 1 0. Yeah. So 1 0. Okay, so now this should work. So we have omega here. So this part is done. Yeah. Again, at the correct location for the constraints for body I. So we are taking into consideration only elements of qi. Yeah. And as arrived, so here I and omega a as I local. Omega a as I local. Okay. We need also the second part. Okay, I have even mouse. We need also the second part for body J. So we also have here body J, and it's with minuses, like put it here, yeah, for obvious reasons. I is I, it's constant, so it's here, there. And here we have just rod Fi of body J and R as J local. This is already invalid. This came from the old. As we can see, we have some warnings because now the code doesn't depend on those terms, so we will just remove them. And this is how the code for Jacobian of the Revolute constraint looks like. Make sense? Any questions? I suppose that when I code it, it looks easy, but when you have to code it, it's a little more complicated. But yeah, when you put it in correct way on paper and understand where its place on the Jacobian and other term, then you just have to, figure out that it's placed properly, yeah? So we can also run here simple checkup that at least that we know that, for example, now after those 5 simple constraints, because we add those terms to our Jacobian, we are expecting to have 6 extra rows for our revolute joints. Yeah, because each of those add 2 entries, so we are expecting to have 2, 2, and 2. Yeah. Ground and crank. So we know at least it's easy to see where those I matrices will be, yeah, because they will be for the ground, so it will be at the coordinates 1, 2, and for the crank is second body, so they will be at position 4, 5, and the next crank link. So for the crank it will be the same. For the link it will be for the next body, and the link slider, yeah. So let's see this in action. Okay, run it again. So we are expecting to have 1, 1 here for the first. Okay, so first 5 are of course still the same. Yeah, we shouldn't override them. So this is the first revolute joint because they go next. Second revolute joint, third revolute joint. We are missing one driving constraint. Yeah. This is for ground. So it's identity matrix and here zeros because it was located at position 0, 0. We can check this in our code. Uh, this revolute joint was put for the ground at position 0, 0, so of course it's 0, 0. Next we have some values for for our crank second body with minuses, and that one depends on the angle, depends on location, but let's say it makes sense because it's within the range of those values. Yeah, you can calculate it by hand if you really want to, because the expression is pretty simple. For the second joint, we are correcting ground and link. So here crank and link. So here crank is with minuses, and here crank is the first body, so it's with pluses. Another expression, it's with the minus because at least this is consistent, because here simply this is with minus because the location of the vector is in another direction, so it makes sense those two are the same. Next we have this minus I, minus identity matrix for link, makes sense, plus some stuff, and again connected link and connected slider. And for slider is 0, 0 because once again we put this revolute joint at the origin of the slider. Makes sense. Is it correct? I cannot truly tell, yeah, if those numbers are 100% correct because I'm not so good in memory with sines cosines, yeah, to calculate it. If I wanted, we just have to go back to pen and paper and calculate it, but at least this looks reasonable, yeah. So let's proceed. The last Jacobian entry is for driving constraint. For the driving constraint, as I tell you, Jacobian doesn't depend on time. It just with respect to coordinates. So this is just leaving out. And simply we get the same like for the simple constraint. So we have here, of course, D. Uh, and it's just 1. Because this one is function of time, it gets 0. This is coordinate at this location, it's 1. I hope why it's 1. Because it's because of the same rule. Yeah. So now we should have the full Jacobian. And now we have 1 here, which is rotation of the crank. Yeah. Ground, crank, rotation of the crank. And here we can see clearly that we add driving constraint to the rotation of the crank. Everything fits together. So okay, so we have Jacobian. We can check that it's full rank, hopefully. Yeah, so it's nice. Uh, because if it's not full rank, then we have some numerical issues and we have to figure it out. Most likely it would came from our errors in implementation. So okay, so we have another point met. We just create this Jacobian. And now we can add this to Git and commit our changes. By the way, okay, I don't know if I should do this here, but in practice, we could also try to numerically approximate the Jacobian. Do you know any function to numerically approximate Jacobians in MATLAB? Also, not, I'm also not sure about this. So let's take a look. Okay, how convenient, yeah. But I don't think that it works that way. Because it just takes one value. But what is f? So it is doing something else because I would expect to calculate it based on the function. Okay. Okay, so this is Laplacian. So okay, I'm sure that we can use it, but it sounds like a little because I should have this kind of the code somewhere. Mm, what happens to it? Okay, because of some reason it doesn't start my OneDrive by default, so I suppose that this is the reason why it doesn't calculate it. Okay, because I would like to, I think it will be also useful for you, so um, uh, to use it, because if we don't want to use numerical Jacobian, we could, yeah, but we really don't want because it's slower, not so accurate, yeah. But at least calculating numerical Jacobian gives us the feeling if the stuff that we have calculated makes sense. Yeah, then we can check. Of course, the error could be pretty large, but it cannot be too large. Yeah, so that's why I wanted to use this. And simply, I remember that I have, implemented more than once. So then I hope that we can use it. But okay, okay. Before it will go, if it will start working, we can try to use interrupts. Yeah, because we have okay, here we have it. So I will just copy paste this code, yeah, into a new function that I will save here. Approximate Jacobian, yeah, as name suggests. So this is only for verification, yeah. So we can see that the function is pretty easy. Because it just contains a vector function. So it's our, of course, so this is the same like here, constraints at time 0. And of course, okay, because I calculate here Jacobian already for Q, but what we have is Q0. So let's also put here Q0, yeah, and let's name it CQ approximation, yeah. And let's see, let's hope it will work. Okay, it works. And if we calculate the norm of CQ minus CQ approximation, we can see that this norm is not super small, but it's relatively small, yeah. And here you can see those two matrices, one by another, yeah. And you can see that for simple constraints, it's mostly 1. However, here you can see that it's close to 1, but not exactly 1, yeah. But all the leading numbers are matching, minus 51, minus 85, the same, yeah. 52, 29, 52, 29, 33 minus 19, yeah. So it's pretty strong indicator that our Jacobian is correct. This error is not small, but this is error of numerical approximation, not of our Jacobian. So this is one of the reasons why this numerical approximation, of course, is great, because you just, instead of writing those Jacobians, we have just one line of code. But, but firstly, it takes some time to calculate it. Of course, we cannot see it because our computer is so powerful. But yeah, good to have a way to verify it. Yeah, because like, again, everything, there are many solutions for most of the tasks. Some are just better, some are worse. Next step. Yeah, so this will be Q from fsolve. And now we want to get Q from Jacobian, from Newton-Raphson. Newton-Raphson has header like that. So let's just copy paste it. Add simple constraint, Jacobian constraints. You want to use here, yeah. So of course this will be Q. Number of iterations is it is what it says, yeah. And now we have to provide fj, x, and tau. Quite few of those, but okay. F is our function, so it's our constraint function, so it's provided here already. So we can say that it's from t equal to 0. So here is t. J, of course, is our Jacobian, yeah. So we have to make it the same way. So it just depends on Q. Function is Jacobian of constraints. Of course, it takes sys and Q. X is our Q0, and tolerance is something. Okay, let's see if it works. Well, okay. Because iteration counter should be positive number, and as you may remember, we set it to a negative number when something is not okay. Okay, so it works. Again, norm of Q, Q minus Q F solve. Very close. We can also calculate simply, check if constraints are met. For F solve. So here we have Q, yeah. Okay, yeah. So they are met. So here they are met at the level of minus 13. Okay, let's run it again, yeah. So here they are met at the level of minus 13. Here they are met at slightly better, but the difference is small. It's like just factor of 2. so it's not a big deal. Uh, let's check if what I say is really true, because if this is really faster, I wonder if this will be able to catch this, because all those computations are pretty fast. Yeah, so we have to calculate. Yeah. So as you can see, solution using Newton-Raphson is like 10 times faster, close to 10 times faster. Yeah, maybe 8. But it's, yeah, for a long time, long running solution, it makes a difference. Okay. So next position on our list is checked. Any questions? Any doubts? Okay. Do we need a break? Hmm? Okay, let's make just a short break, like maybe just 5 minutes. Yeah. Okay. So let's make a 5-minute break. Okay, perfect. So we are back here, and our next task is to run our position analysis in time. Yeah. So uh, I can see that I forget to add this file. So the part of the code won't work. So let's fix all that. Okay. Okay. Now then I will push the changes. Uh, so yeah. So now we have it done in the way that we just calculate it once, yeah, and it's clear, yeah, because we wanted just to see if it works. Yeah. So we just calculate it once and we calculate it for t equal to 0. But we want to solve kinematic analysis. Yeah. And then we want to make some plots possibly, yeah. But first we want to solve some kinematic analysis, yeah. So again, I will just write a header for our function, yeah. But for this function, we for sure want to get some time, yeah. We want to get Q, yeah. So Q will be the matrix that has coordinates for given time. And the function will be simply kinematic analysis, yeah, of the system. Yeah. Now it depends how we, for example, because we want to have it for a specific time. Yeah. So not to overcomplicate, we can just define that t is equal from 0, 0, 0, 1 to, let's say, start with 1. Yeah. So we will just put here q and sys t. Okay. Can we solve it that way? Yeah, why not? Yeah, and yeah, let's do it. Again. Okay, we want to get Q and for our system in time. Yeah. So without getting into too much details, of course, we want to have Q. Uh, okay, I think that one thing is missing here, or not. Should we encapsulate everything in kinematic analysis? Why not? So first Q0. So how we get our initial coordinates? It should be somewhere here. Okay. assemble coordinates for our system. So Q will be zeros of, it will be matrix, yeah? So how should we organize our coordinates, in columns or in rows? OD organize it in rows. So let's go with rows, yeah? Okay. So the first will be length of Q0, and the second one is length of time. Okay. And the easiest implementation would be for t in for t equal time, and now we need to solve it somehow. Yeah? It's not a good one because we need indices here. So let's refine it. So let's put length of time here. Yeah, then we can put it here. And then instead of going through time, we can go to 1 to n time and then get t from time and I. Now we have to get what we already have done, like here. Or even that part. So we want to get Q from Newton-Raphson method is defined, T is from here, Jacobian system is provided, Q0 and tolerance. So let's leave it total tolerance. Simply if iteration counter is smaller than 0, we will put error. That kinematic solution on position level for t equal to does not work, and t. Okay, hopefully we will never get there. That one here? No. No, because it's still a vector. Yeah, so it's not capital Q, yeah. So, but of course it's not finalized because here, after everything is done, you can write that Q for everything and II is equal to Q. Yeah. So, yeah. So then we'll store it all that stuff in that way. Okay. So that's why, because this is still from this is still Q. Let's say II. Yeah. So this is just Q for given time II. Like here we can say that this is also TII. This Q0 is incorrect here. Maybe it will work, but it's not a good solution because Q0 is simply the initial coordinate and we are marching in time, so the configuration of the system can change quite drastically. So as we talked earlier already a few times, that Newton-Raphson is best on finding solutions that are close to what? To the initial solution. Yeah, of course. That's why we have to update it, because we can run into errors that our solution won't be continuous. Because as we discussed, yeah, for some mechanism, in practice, many of those mechanisms, for just given set of constraints, we can have multiple solutions. So it can happen that we get into some kind of position that starting from this initial condition, we will get incorrect solution, or we won't even find it, you know. At best, we would get too many iterations to find our solution. At worst, we will we won't be able to get solution or get some solution that it's not correct one. Yeah. So here we should write that qii is equal, for example, to q0, and then here use qii. Does it look like correct solution? Because here we just store first value, then we use this value in the function. This value in the function is copied there, of course, so it has nothing to do with function here. But this function will return another vector that we will put it in the same name, but it will have different numerical values, and then we will store it and repeat. Yeah, so all the time we'll have here correct initial value. Maybe it's not the best. Maybe I will use Q0II just to avoid confusion. Q0II, and here to repeat with iteration, I will use also Q0II is equal to QII. Yeah, this makes it maybe more obvious how it is used. In either case, this should work. Yeah, and hopefully it won't give us any errors. So let's see. Okay, so we are here, so just let's run it. We get some Q with some numbers. We have T. With T, we generate by ourselves. Good, no errors. So it means that, you know, all the points were met. Yeah. Let's take a look if all this make any kind of sense. Okay. So plot T Q of it has size. So for example, 1 and all. Yeah. Yeah, it is. Yeah, but still, you know, we I think that maybe let's make it a little thicker. Let's try. Okay, it's a little thicker, yeah. So it's 0, yeah, but it should be 0. Yeah, so of course, yeah, so it's ground and we are expecting this. The same applies to 2. We're expecting it to be 0, yeah. And the same applies to 3. We're expecting it to be 0, and it is 0. So it's nice. Now let's get to crank. It's something nice. It's also something. We get some solutions. Does this solution make any sense? This looks fine, yeah, at least, because this is angle of our crank. Yeah. And we are expecting our angle of our crank to start at minus 30 degrees and decrease by 1 radian per second. So after 1 second, we should get, 1 radian less. So at least this looks correct. Yeah. But what about others? Hard to tell. Yeah. Can we do something about this? Of course we can. Yeah. Because going back to our mechanism, we are expecting our mechanism to move in certain way. Yeah. So we are expecting it that the center of the mass of the crank, for example, will move that way. Yeah. And so can we see this? Yes, we can. Because we can plot just in very easy way. This is the easiest plot that we can do, center of masses of those points. Of course, we can calculate all those points because we have the tools to calculate it. But just based on the Q, we can plot where are center of the masses and how they are moving. Yeah. So we can make a plot of Q for um, 1, 2, 3, of 4 and all. Then it will be Q of 5 and all. Yeah. Then we can make that X label is X position in millimeters will be it's Y label. It's Y position in millimeters. Of the crank. Yeah. We can make it even even in slightly different way because we can get okay, okay, let's not overcomplicate it. Then we can try okay, so we can try to make this line thicker. Then we can apply axis equal maybe it will be possible even to add I don't know, let's see if this will work. Zero, zero. Yeah. So here is center of the world or the location of our. Can you see this plot? Well, or should I? Can you see it? So this is kind of center of our world. So this is in either term. What is this? Location of our global coordinate frame. Yeah. So we have a crank located here. So this is 0, 0. So like here. Yeah. Center of our world. Yeah. And what this curve shows, yeah, this curve shows how center of mass of our crank is moving. Yeah. So it doesn't have arrow, but you can guess that it starts from here and goes to there. Yeah. Does it look correct? Looks more or less correct? Yeah, it looks more or less correct because first of all, we are expecting that this line is on the angle of 30 degrees. And it looks like 30 degrees, pretty well, yeah. And then, according to definition, we are expecting that this point will move here. Okay, it's 1.2 radians per second, so it's interesting. Have we put 1.2 or 1? 1.2. So, okay, why not? Okay, so it moved into correct direction because should move that way because this is how we apply our angular velocity. Uh, Next observation is that it looks like a circle, and it should looks like a circle, yeah. So it looks like an arc, and it should be like an arc, simply because this distance from with respect to this point should be the same, yeah. So it looks pretty good. Yeah. Now we can do the same for different center of masses, yeah? Because if this point moves that way, so how we are expecting this point to move? So this moves up, yeah? Or moves also that way, yeah? So this point should move also up and in this direction, yeah? So it should move like something like that, I suppose, yeah? Let's plot it. It's easier to say what crank will be doing because it has to move in the line, yeah? But let's plot it. So let's plot it for so 6, so it should be 7 and 8. And also let us plot not 9 and 10, but 10 and 11. So we will have position of the crank. We have added link. And slider. So slider moves from here to here. Makes sense. Yeah. According to what should move, yeah. So this moves that one, this moves here, and also it makes sense for the link, yeah. It moves in right direction as we are expecting because following this, and it moves a little up because of those as the link will shift in this direction, yeah. It moves both in on right and both up, so it looks reasonable, yeah. Then we could make even animation out of it, but I don't think that we have time for it. Yeah, maybe. But to create an animation is a little more involving. And we still have at least one goal to do: velocity analysis in time. Yeah. So we add position analysis. What we need now, velocity analysis in time. Fortunately for us, velocity analysis is pretty straightforward. Yeah, because as I have put it already here, yeah, time derivative of constraint vector is partial c partial q times q dot plus ct, partial c partial t, yeah. and it's written here, just in just in the arrange way. Yeah. So this is directly equation c equal to 0, c dot equal to 0. So that way you have Jacobian times q dot is equal to minus ct, because ct just moves to another side of the equation. Clear? This is of course our Jacobian, so no issues here. Uh, we just need this part. As you can see, it's 0 with CQ, because like none of those geometrical constraints like leveled, simple, or transitional depends on time, so it's simply 0. It's non-zero only for driving constraint. So because this equation is simply equation c dot equal to 0, yeah, and our driving constraints, no, it was driving, where we put d here, was just qi minus f of time, yeah. So that we said that's specific coordinate, in our case the angle of the crank follows some function of time. So c times of d is of course equal to qi dot minus f prime of t. Yeah. This part is of course c d q times q dot, because as you remember Jacobian is identity here, so it holds. And this part is just ct. Yeah. So we have to implement ct. Yeah. So get back again to our constraints. So let's make constraints dt. Okay. So constraint with respect to t. Let's call it t. Let's save it. Of okay. Ct has the same size as c, because it's just a vector, because we are calculating partial derivative with respect to scalar t. We know that for a simple constraint we have no, it's 0, because it doesn't depend directly on time. For revolved joints it will be the same, it's 0, so this is valid only for driving constraint. However, here we have coordinate function t, and we need not coordinate, but we need derivative of this coordinate function t. Yeah. So we have to get this coordinate, this derivative. Yeah. Now there are many ways of getting this, but the easiest will be to get it by hand. Yeah. So like here we are adding this driving constraint, and we are adding here this function of time. We can either put here it by hand, that we will derive those derivatives, or we can calculate it using this symbolic toolbox here. But those expressions looks pretty simple, yeah? So let's just calculate it by hand, okay? So let's here add two extra stuff, yeah? So let's here add not only this function with respect to time, so that says where are our coordinates, but also add velocity equation, and we can also add acceleration equation. Yeah, why acceleration equation? Because the next goal is acceleration analysis, and as you can guess, acceleration analysis is based on c double dot. And c double dot will have f double prime. Yeah. So let's add here function that it's f prime, which in our case it's simply omega. Yeah. And let's add here uh, yeah, double prime, which is 0. Of course, it won't work because we cannot just add something. We have to open here and add coordinate function. So we will have also okay, works. So we have add coordinate, velocity, and acceleration, and we will just store it here. And now we can use it. Because we store it, we will add it here, and then we can use it in different parts of our program. Like here. Yeah. So of course, partial C, partial Q, partial T is 0, because it depends on time, but not explicitly, just implicitly. And here we need which is coordinate velocity. Tada. Works because it must work. Yeah. And in our case, it doesn't depend on Q even. Any questions? Make sense? Yeah. No. No, because the differentiation rule is slightly more involving. Oh, but we will get to this very soon, like in 5 minutes. Okay. But okay, so this is done. We can add this file. We can add those two files to Git. And now we can modify our kinematic analysis just to return also solution for time. Yeah. So we was returning stuff for position. Now we can also return this uh, Q prime, for example. Okay. Which contains also velocities. Yeah. So Q prime, 0, length Q0, and time, because this is exactly the same. Yeah. And now we know that now position analysis is done. Perform a velocity analysis. Yeah. So for velocity analysis, we are using this equation. Yeah. So we need CT that is equal to our function now. So it just depends on sys and time in our case. So Q prime at time I is equal to what? It is equal to minus CQ, I think, over CT. I think this goes in this direction. It won't work because we don't have CQ here. It's calculated inside this function, but we haven't calculated here. So let's just fix it and calculate. CQ is equal to uh, that part. And of course, Q in our case is QII, because this is our current time. Here we have the CT. So we have, this is the way to calculate CQ, Q prime. Yeah. So just based on this, just based on this equation, we put this on the other side, yeah, and we have minus here. Make sense? Here we need two more lines to get acceleration analysis. So we need to calculate the same right-hand side of your acceleration analysis and then just solve it for Q prime prime. But okay, so Q prime of so let's store it. And now we will use it here as well. Because we know just by using this approximation for the position based on the other position, so just this simply goes to Taylor expansion, yeah, because we have used here just location, but we know that we can get even better if we use approximation for velocity, yeah. So we can use here, get here that dt is equal to t of 2 minus t of 1. Let's assume that this time constant, the time shift is constant, yeah. And now here we can add q prime I times dt, yeah. And here we can add also the term for acceleration, if you will have term for acceleration, yeah. It's just 1/2 t squared, dt squared, times q prime prime, yeah, in the same way. But okay, so now we can go back to here and here. So from here we can get q and q prime. Let's run it. We get an error. Error here. I believe that it comes to this, that we call it different way. So it's time. So let's run it again. Okay, looks promising. We get no error. We get our plot. And now let's do the same plot. Plot on plot. So let's plot the velocities. Yeah. So here we can just leave 0, 0. So it won't complain. So we have q prime, q prime, q prime, q prime. So here is 0, 0. So now it's great question, does it make sense? So first of all, the description of the axis is misleading because now we have here millimeters per second. Here we have velocity of the center of the world, yeah. So in our case, our center of the world is not moving, not like our world, but at least this one is not moving. Yeah. So our world is standing still, and we are sitting there and observing how other things are moving. And now the question is, does this make sense? No. No and yes, depending what. It should be minus 5.2 for phi. Yeah. But here, we have this complex motion. So this is the velocity of your point moving on the circle. And the velocity for the point of moving on the circle, and like here we have point that it's moving with constant velocity, is the velocity that is going inward to the center, yeah? So, mm, so does this make sense? No, it's not moving to the center. What I'm talking about, this is the vector that is, just perpendicular to the position. Acceleration moves to the center, yeah. This is the vector that is perpendicular, tangent to our path, yeah. Okay, let's make those two figures, and maybe so let's plot this, and let's make it a new figure. Great. So now we have, yeah, but we can do it visually again, yeah, because what we are expecting, the velocity here will be this kind of the vector, and the velocity of the here will be this kind of the vector, yeah. And we can see that velocity is this kind of the vector at start, and then the end is this kind of the vector, because this is end of this vector, yeah. Because in practice velocity is, yeah, so it makes sense, yeah, that this is velocity of this point, because it will be here, it will be that vector. Of course, we will move it to 0 because it just velocity is just a vector, yeah. So its origin will be at 0 because we will just get, well, where is end, yeah. And the beginning should be here, but we didn't bother to transform it, so we just transform it to 0. So we just here, yeah. So looks fine, correct? Same here. It should be this kind of the vector at the start and this kind of the vector at the end, and make also is similar, yeah. Once again, the easiest is for the crank, not crank, slider. Okay, for the crank it's also pretty easy. For the link it's more complicated. But for the crank, it goes here and here. So cranks moves in this direction. So it should be a vector that starts at 0 and ends somewhere at the positive point. And it has only one coordinate. So at least it looks reasonable. Not sure where is the end, what is beginning. But it also looks pretty correct. Okay? The same you can do for acceleration analysis in practice. Yeah, because the acceleration analysis, then here, those vectors that came from the velocity are acceleration analysis, results of acceleration analysis. And what you have said about this, uh, is shown here. That of course, once again, velocity of the ground is 0, those velocities are also zero because slider is not rotating, neither moving in y direction. And this should be constant, and all the time value to minus 1.2. So here we can see. Yeah. And also we know what is this norm, because this norm, what should be this norm? As far as I remember, it should be equal to omega r. Yeah. So it should be equal to 1.2 times this 100. And we can all check it very easily. Yeah. So firstly, we can plot as well t q prime of 6. Where is this plot? Okay, I press incorrect button. Yeah. So it's minus 1.2. Here we can see some very small deviation, but with respect to z, numerical accuracy, it's minus 1.2. And then we stated that qp4 squared plus qp5 squared, and let's calculate square root of it. 120. 120. No surprises, because all this comes from physics, from mechanics that we know from mm, old times. Yeah. And it works. Yeah. There's even another way, of course, to calculate this with finite differences. Yeah. So for example, if you are interested, if this makes sense, yeah, we can calculate this using some simple finite difference scheme. Yeah. Plotted in that way that we have t 1 to n minus 1, because on finite difference we will lose one sample. Right? So it's q p of 10 from 2 to n minus qp of 10 1 to n minus 1 . So this is this value. To have finite difference, we have to divide it by our time step. And our time step is here, is 001. So this must be divided by 001. And we want to compare it to t qp of 10. So I make a mistake because here I calculate acceleration, or approximate acceleration using finite difference, because it should be based on q, of course, yeah, because velocity in finite difference is based on position. Looks pretty close. Of course, finite difference is not the best way, as we also do not have here super fine grid, but can you see those? They are pretty close, yeah. So our solution looks pretty solid. Yeah, so first of all, you can just interpret the results based on visually, like we have done. Next, based on the motion of the point that moving on the circle. Yeah, we know what the vectors should look like. And here we can also verify it numerically using finite differences. One version of the finite differences. Is this all clear? Okay, great. Any questions? Okay, so we have done what we should have done, and we are even on time. So it's really nice. So now it's your turn and go to acceleration analysis. Because we have Jacobian, you just need to calculate this small term g. Okay? Yeah. So it's better to good understand how this was done. Yeah. But in the last resort, if you will go for, I close it somewhere. No, I think I have it here. Yeah, you cannot use this directly. You can use this and this because those are coordinates, but those are transformation of the coordinates. So we have to get back to coordinates and write again that d is clearly this vector minus this vector. Yeah. So because this points to different points, it will be clearly a vector. So it will take derivative of this will take the similar form like for revolute joint. And if you get this vector, which is of course constant, yeah, in one, so to get n, it's simply ai times n local. And you know how to get partial derivatives or any kind of derivatives of this kind of expression. Yeah. Okay. Yeah. So this doesn't look very trivial, but here is the way how to get it. Compute c double dot, neglect acceleration terms, and negate. Why? Because acceleration terms are here. So because this equation is in another term is c double dot equal to 0. Yeah. So if this is c double dot equal to 0, so and here on the left hand side we have acceleration term. So if you remove acceleration term and you negate it, you will get all the stuff that is on the right hand side. Make sense? I suppose that is all many things that I'm talking is easier to say than done. Yeah. But simply, let's say that we consider this what constraint let's say that we'll consider uh, at start to start easily this driving constraint. Yeah. So of course CD is equal to Qi minus f of t. Okay. Q is element. This is just one equation. Qi is one of the coordinates. Ft is just function of time. Yeah. And we know that we have c double dot equal to 0, and this is equivalent to cq. So those are vectors. This is matrix times q double dot equal to g, and g is just vector. Yeah. So we know what is cq, of course, because it's our Jacobian. Q double dot is our unknown. So to get all this, we need g. And here is said how to calculate it. Yeah. So c double dot. So of course, to have c double dot, let's calculate c dot of d is equal to qi dot minus f prime of t. Clear? Yeah. So c double dot of d is equal q double dot I. Okay, not here I. Minus f double dot of t. Clear? Yeah, so this is the first step. The second step is to neglect all acceleration term. So we are neglecting that because it's included in here. So we are neglecting this part. So we know that the g for driving constraint it's simply f prime double prime t. because we get what has left and we negate it because we move it to another side. So this is just G expression for driving constraints. We can clearly see from this that pretty obviously G expression for simple constraints is 0. Yeah, because there is constant, it will be immediately be go out of the scope. So of course it's slightly more complicated for revolved joint. Yeah, it's written here. Yeah. But I hope that you maybe remember that R double dot, because R is just position, takes this form. Yeah, so it's R double dot plus this minus this. You can check it on our previous slide. Yeah, so I won't repeat it. So if you have CR with that stuff, and if we calculate C double dot R, it simply takes this form. Any doubt? I hope not. Yeah. So now to get G, we are neglecting acceleration terms because they will appear on the other side, yeah, and G cannot depend on accelerations, yeah. So we can just neglect, okay, so maybe it's a little too long, but okay. So we can neglect this stuff, we can neglect this, we can neglect this, and we can neglect this. All those are acceleration terms, yeah. Here is acceleration, here is acceleration, here is acceleration, here is acceleration, yeah. By the way, you can clearly see that because Jacobian was identity times identity at the first position, so this is identity times R double dot, yeah, and this is clearly part of the Jacobian times phi double dot. So all this matches. So we are left with this term and with this term as only non-zero candidates for G. So to get G, we take this here, and put minuses. And we end up with this expression. So if you implement this in your G vector, together with this similar stuff for simple constraint is just 0, so this is trivial. For this driving constraint, you have just second derivative of time derivative, of second derivative of your time function. Here you have that part, and that's all. And with this expression for G, you can use this equation, so CQ times Q double dot equal to G, and then you get Q double dot. And this ends calculation of your acceleration term. And as you can see, it means that also G depends on coordinates, velocities, and because of the case of driving constraints as well on time. Yeah, so this is also the reason why we have to first solve position problem, next go to velocity problem, and at the end follow with the acceleration problem. Repeat, get hold of the solutions, make plot, check with finite difference if it works, and you are done. After all that, you can change this and this to reassemble different mechanism, press enter, and everything will be calculated automatically. Any questions? No. And it's almost never constant. Because as we spoke, and when you have this n is written in global, yeah. So uh, where are those? Yeah. So so n is based on some vector. So it's so ni is ai ni. So of course this is constant, yeah. But you have to transform this constant vector that is written in your body I. So this vector is of course constant in this body, but this body can typically rotate, yeah. So so yeah, so for this expression it's not constant, yeah, because it's just you just okay, you just use this transformation. So and that is simply ai dot, so it's equal to this omega a times phi I prime. And the same with similar with the second derivative, yeah. And it's very similar what we have already done because it's already like here, yeah. So this is the second derivative of this n. I mean, it takes exactly that form. So that's why there's no new stuff there. If you take a careful look on it. Okay, perfect. Any questions? So what we will do next time? Dynamical analysis. Because you know that m times a double dot a is equal to f. Yeah. So then we can, of course, move from this expression to expression for rigid bodies, that mass matrix times q double dot is equal to appropriate forces expression. And this can be already integrated in time. But we'll get to all this theory and implementation and solution of ordinary differential equations and how to transform differential algebraic equation to ordinary differential equations in the next following weeks. Okay, so we have no more questions, so thank you for this session in ends where it was planned to end, and yeah, let's proceed as usual. So thank you again, and yeah, see you next week.